When looking at certain compounds, the molecular geometries do not make total sense for the locations of the valence electrons in the atom. For example, with beryllium fluoride, the valence electrons on beryllium are in s orbitals. However, the valence electrons that are unbonded and able to form bonds between atoms are in the p orbitals. In order to solve this problem, the electrons in beryllium, which in their ground state look like this, share energy between the orbitals around fluorine to promote one of the electrons from the s orbital to a new p orbital, to then allow for the bonding between a fluorine and a beryllium. This process is called hybridization, and through this process are formed hybrid orbitals. During the process of hybridization, it starts where one of the electrons on an s orbital are promoted to a p orbital, which then leaves two unbonded electrons, allowing for the formation of two bonds. However, this would only allow beryllium to form with one fluorine. So in order to solve this problem and allow it to bond with two, the s orbital and the p orbital mix together to form a new orbital, a hybrid orbital. These hybrid orbitals act in a similar way as s and p orbitals do, acting as a hybrid of the two, which is why they're called hybrid orbitals. After hybridization, the orbitals look like this, with the already pre-bonded orbitals that already exist and the valence orbitals all being reformed into sp orbitals for this example. For other ones, they can be formed into sp2 or sp3. The number of hybrid orbitals around the central atom is the same as the number of orbitals around the central atom to begin with. So for beryllium fluoride, after hybridization, it would have two hybrid orbitals. There are three types of hybrid orbitals, but certain evidence has disproven the third type. So the first type of hybrid orbitals is sp orbitals, which is the hybridization between one s and one p. So it somewhat looks like, on the atomic scale, to be a s orbital plus a p orbital, and then after hybridization, to be a tiny little loop and a big loop. And then of course when they are together, the two sp orbitals, once they're together, they just look like this, with the little tiny loops being in there, kind of like a little bow. And these hybrid orbitals are only found with linear geometries. The next type are sp2 and sp3 orbitals. So sp2 orbitals are the hybridization between one s orbital and two p orbitals, which is why you get the little 2 up there. So on the molecular scale, they look like 1s plus 1p, and then another p. And then when they're together, they sort of look, in a sense, like that. I know that. Yeah, I'm going to redraw that. Sort of like that. And these hybrid orbitals are only found with only tridimensional geometries. sp3 orbitals are the hybridization between an s orbital and three p orbitals. That's what this looks like. On the molecular scale, they look like an s orbital plus or 1, 2, and 3 p orbitals. And then after hybridization, we have our 4 sp3 orbitals. And then all together they kind of look. I'm gonna draw this. I hope that looks somewhat decent. I'm gonna redraw that. Looks somewhat like that, which is for tetrahedral geometries. For molecules where the electron domain geometry is trigonal bipyramidal or octahedral, that is type 3 hybrid orbitals, and since there has been evidence disproving it, it's not to be worried about. So, hybrid orbitals and hybridization help explain how the molecular geometries that we get from VSEPR are possible by showing how the electrons on the bonding atoms would change to help overlap orbitals in order to form bonds between other atoms. To determine the hybridization of a compound, you start by drawing a Lewis structure, then determining the electron domain of the molecule, and then using that to find the hybridization for that molecule. So, for example, let's go with finding the hybridization for methane. So once we've got the Lewis structure drawn out, we can then determine the electron geometry, which we can see as we have 1, 2, 3, and 4 electron domains around our carbon. We can tell that it's going to be a tetrahedral electron geometry. So tetrahedral electron domains are always sp3 hybrid orbitals. So that is how you determine the electron domain. No, that is how you determine the hybridization for a certain molecule. So the hybridization for each electron domain geometries goes as follows. Linear electron domains have sp hybridization. Then trigonal planar electron domain geometries have sp2 hybrid orbitals. And then tetrahedral electron domain geometries have sp3 hybridization. One way I remember is by remembering that linear molecules have 2 electron domains around their central atom, and there are 2 orbitals with sp hybridization. And trigonal planar, there's 3 electron domains around the central atom, and there are 3 orbitals. And then for tetrahedrals, there's 4 electron domains around the central atom, and there are 4 orbitals. For some extra practice, find the hybridization for these 3 compounds. These are the hybridizations for each of these molecules. For some extra practice, find the hybridization for each of the carbons in this molecule. So the hybridization around the first carbon is sp2, as it is a trigonal planar electron domain, and then the same thing with the second one with an sp2 hybridization. Our third carbon here has sp3 hybridization, as it has a tetrahedral electron domain. Our fourth carbon is an sp hybridization, as it is a linear electron domain, and then the same with the fifth one, with also being an sp hybridization. And then then the sixth carbon and final carbon is an sp3 hybridization because of its tetrahedral electron domains. And that about sums up hybrid orbitals.